Hello everybody, I'm Pedram Pad from CSTM Switzerland. I'm going to present our paper called Efficient Neural Vision Systems based on Convolutional Image Acquisition. Substantial progress has been made in deep learning in recent years, but the advanced approaches still remain computationally expensive. In fact, vision applications often require large architectures in terms of both number of parameters and computational cost, making them unsuitable for low-power applications running in resource-limited devices. Recently, ideas have been proposed to partially or fully outsource the neural network computations from the digital processing unit to the optical frontend in order to decrease the computational cost. In fact, imaging an object through an optical system can be seen as a convolution with the PSF of the optical system. So by engineering the PSF, we can benefit from this inherent transformation happening in optical domain. The advantages of this method are that it consumes no power and also takes effectively no time. The methods based on these concepts can be split in two classes. The first ones use phase masks which act on the phase of the wave of the incoming light. One of the major drawbacks of these methods are that they require a coherent monochromatic light to function properly. This condition does not hold in natural scenes, which results in chromatic aberrations that dramatically degrades their performance and thus makes them unsuitable for practical applications. The second class is the methods based on transmission masks which act on the amplitude of the incoming light. These methods are also called coded aperture and used for applications such as deblurring, template matching, and depth estimation. However, these methods usually rely on low-resolution patterns without an end-to-end data-driven optimization. In this work, we propose a generic approach for optical convolution based on high-resolution transmission masks that are suitable for practical machine vision applications. The mask is tailored for the application at hand in a data-driven fashion. The light emitted from the object passes through a two-lens optical setup having a coded transmission mask at a certain point in the middle of two lenses. The convolution of the scene and the mask reaches the image sensor. Therefore, what is received on the sensor is not a raw image anymore, but a feature map which is the outcome of the convolution of the scene with the designed mask. At the readout step of the image pixels, during the analog to digital conversion, a linear or nonlinear quantizer can be used. In the paper, we show that using a nonlinear quantizer improves the performance without imposing any computational cost. After reading the pixel values, we feed them to a neural network to perform the next steps of the inference. The scene, the transmission mask, and the received signal on the sensor are depicted here for two examples of the masks. We can implement several filters on the same mask by leaving enough blank space between them to avoid overlap. However, notice that having several filters or kernels can be seen as a special case of a large kernel without the blank space constraint. So in our training, we just chose a filter with high resolution and let it be trained based on the data. It is worth mentioning that due to the large number of free parameters of this kernel, its output can be very rich in terms of information. We utilize this idea to design an ultra-efficient classification system for OCR. For the processing unit, we selected Sentient NDP101, which is an ultra-low-power ASIC for a fixed neural network comprising 4 fully connected layers. For the image sensor, we chose the ultra-low-power image sensor Ergo, which provides both linear and logarithmic quantization of the pixel values, and we chose the optical mask size of 240 by 240. We trained the mask and the weights of the sentient network for the extended MNIST dataset. As we can see, by using the proposed idea, we can get an almost state-of-the-art accuracy with more than 2 orders of magnitude less computational cost. Here we can also observe the added value of using optical convolution and logarithmic quantization by comparing the performance of the full system with the system comprising only the fully connected neural networks inside the sentient chip. More detailed results and also results for the application of hand gesture recognition can be found in the paper. With this, I would like to thank you for your attention.